Chapter 3, Section 3, States of Matter. Key ideas in this section: how do fluids exert pressure? What force makes a rubber duck float in a bathtub? What happens when pressure in a fluid changes? And what affects the speed of fluid in motion? So, fluids exert pressure evenly in all directions. Pressure is the amount of force exerted per unit area of a surface. For example, when you pump up a bicycle tire, air particles constantly push against each other and against the walls of the tire. So pressure can be calculated by dividing force by the area over which the force is exerted. So the formula for pressure is P equals F over A. The SI unit for pressure is the Pascal, and a Pascal is equal to the force of 1 Newton exerted over 1 square meter. And the symbol is capital P lowercase a. And here's a video.
Air density. And there's another important quality of fluids, one that scuba divers and mountain climbers think about a lot: pressure. In our last episode, we defined pressure as applied force divided by area. It's measured in units of newtons per meter squared, known as pascals. And fluids apply pressure in every direction. So right now, there's air putting pressure on you and me from every side. In fact, the average air pressure at sea level is 101,325 pascals. And if you jumped in a pool, the water would also exert pressure on you. But if you've ever tried diving to the bottom of a pool, you'll know that there's more pressure at the bottom than at the surface, which is why at the bottom your ears hurt and your head feels like it's about to implode. That's because the deeper you go, the more fluid there is above you, with its weight pressing down. There's an easy way to...
So the next topic we're going to look at is buoyant force. All fluids exert an upward buoyant force on matter. When you think about buoyant force, think about the first few letters of this buoyant word, buoy. And a buoy is something that floats. And so buoyant force is dealing with the force that keeps an object either immersed in or floating on top of a fluid. Here's another video.
So we have one more property to talk about when it comes to fluid at rest, and it's the one that supposedly made that guy run naked through the streets yelling Eureka! That guy was Archimedes, and he lived in Greece in the 3rd century BCE. Legend has it that he was asked to find a way to figure out if the king's crown was pure gold, and the best way to do that was calculate its density. Archimedes could measure the crown's mass easily enough, but he didn't know how to find its density. He was taking a bath one day when he realized that the volume of the water displaced by an object is equal to that object's volume. And since he already knew the crown's mass, that meant he'd be able to find its volume, and therefore its density, just by putting it in water. That's when he did the whole running through the streets naked thing. So Archimedes discovered that when you put something in a fluid, the fluid's volume increases by the amount of the object's volume. This tells us a lot about what makes objects float or sink. For example, say you have a tub of water and 2 balls of the same size, but of different densities. Say one is an American-style billiard ball and the other is a racquetball. We're going to gently place the balls in the middle of the tub, let go, and explain what happens to them. But first, let's talk about the forces acting on the water that's occupying the space where we're going to put them. Picture a sphere of water within the volume of water that's in the tub. What are the forces acting on that watery sphere? Well, the force of gravity is pulling it down. And since the sphere is in static equilibrium, there must be some force pushing up on it, counteracting the force of gravity. We call that force the buoyant force, and it comes from the fact that water pressure at the bottom of the sphere is greater than the pressure at the top. Now let's put the billiard ball where the sphere of water used to be. What are the forces acting on that? The force of gravity that's pulling down on the billiard ball is stronger than the force that was pulling down on the sphere of water. That's because the billiard ball is denser than water. So even though the ball and the sphere of water have the same size, the ball is much heavier. But the buoyant force on the billiard ball is exactly the same as it was on the sphere of water, since they're the same size and shape. That's Archimedes' principle. There's a buoyant force pushing upward on objects in water, and it's equal to the weight of the water that the object displaced. The billiard ball weighs more than the sphere of water that it's replacing, so there's a net downward force on the ball, and it sinks to the bottom of the tub. But if you were to fill that sphere of water with a racquetball, the opposite would happen. In that case, the force from gravity pulling it downward is weaker than the force pulling down the sphere of water, but the buoyant force pushing upward is still the same. So there's a net force upward on the racquetball, which is why it floats to the top of the tub. Some of the racquetball will pop out of the water, but some of it will stay under underwater. In fact, once it stops moving, the racquetball will displace a volume of water that weighs exactly as much as the ball. Because at that point, the buoyant force pushing the racquetball upward and the force of gravity pulling the racquetball downward have the same magnitude, so they cancel each other out. Thanks to Archimedes, we know why objects float and sink.
So continuing on that, Archimedes' principle is used to find the buoyant force of an object. Buoyant force on an object is in a fluid is an upward force equal to the weight of the fluid that the object displaces. And so when she was talking about the racquetball or the billiard ball in a tub of water, that's what she was showing, is that it's the buoyant force is going to be a certain amount for how much water that it pushes out of the tub or displaces. So another example, if you catch the water that is displaced, an object is lowered into a container of water. If you catch it, when the object is completely submerged, the weight of the water that's pushed out is going to equal the weight or the amount of the buoyant force acting on the object. And so looking at this picture, there's some different things going on. First off, you have this shell that has sank to the bottom, so it doesn't float at all. The weight, and then in this scenario, when something sinks all the way to the bottom of like the lake or whatever you're talking about, the weight is greater than the buoyant force. So for the shell, if the weight is greater than the buoyant force of the shell, then it will sink. In the next scenario, you have this fish that's kind of in between. So it's just suspended or immersed in the water, and it kind of hangs out in the middle of the water. In this case, the buoyant force is equal to the weight. And so they kind of hang out in the middle. And then this seagull, I guess is what it is floating on the top of the water. And if something is floating on the top of the water, then that means the buoyant force is greater than the weight. So an object will float or sink based also on its density. If an object is less dense than the fluid in which it is placed, it will float. And if the object is more dense than the fluid in which it is placed, it will sink. So with this, density is mass divided by volume. And so we can't necessarily change the mass of something, like in a ship. You're not going to be able to change the amount of mass in it besides maybe like how much cargo it carries. But you can change the shape and thus changing the volume, the amount of space that the object takes up. So a block of steel is denser than water. A block down here would sink. But if you shape that block of steel into a hollow form that takes up a lot more volume, then you're going to reduce the density altogether, and you can get a situation like this where you have this huge, huge, huge mass, like a ship, that can float. Pascal's principle states that a change in pressure at any point in an enclosed fluid will be transmitted equally to all parts of the fluid. In other words, if the pressure in a container is increased at any point, the pressure will increase at all points equally by the same amount. So Pascal's principle is shown mathematically by this formula. P1 equals P2. So pressure 1 equals pressure 2. And so because pressure equals force divided by area, Pascal's principle could also be written out as force 1 over area 1 equals force 2 over area 2. So force over an area before you're pressing on something or applying pressure is equal to force over area afterwards. And so when we're talking about Pascal's principle, we put this to use with hydraulic devices. Because pressure is the same on both sides of the enclosed fluid, you can use a small force on a small area to produce a large force over a larger area. And there's a video clip that's going to show that in a little bit. And so the plunger would travel through a larger distance on this smaller side, but it will then end up pushing with a much greater force on the side that's lifting the car.
meter down. The water in the pool could be one example of a confined fluid, because if you had a piston the size of the pool's surface and used it to push down on the water would have nowhere to go. And back in the mid-1600s, French physicist Blaise Pascal realized something about the way pressure worked in confined fluids. If you apply pressure to a confined fluid, the pressure in every part of the fluid increases by that amount. If you have water in a cup and you use a piston to apply 10,000 pascals of pressure to the surface of the water, then the pressure everywhere in the water increases by 10,000 pascals. Today, that concept is known as Pascal's principle, and it's the reason hydraulics is so useful. Say you have some water in a tube with pistons on either side. Pascal's principle tells you that if you use the piston on the left side to apply pressure to the water will exert the same pressure on the piston on the right side of the tube. And the pressure is equal to the force divided by the area. So say you have another tube that's more of a cone shape, with a piston on the left side that has an area of 1 meter squared, and one on the right that has an area of 2 meters squared. Again, you apply 10,000 pascals of pressure to the piston on the left side, meaning 10,000 newtons of force. But the piston on the right side has double the area. So for the pressures to be equal, the water has to apply double the force to the piston as you apply to the water. And so you end up with 20,000 newtons of force on the right side piston. This is a huge deal. You're doubling the input force, but you didn't have to put in any extra effort. And the bigger the difference in area, the more extra force you get. To put it in maths terms, the ratio of the output force to the input force is equal to the ratio of the output area to the input area. Systems like hydraulic lifts take advantage of this by having big differences in area on either side of the fluid. So if you want to apply a lot of force to lift something heavy, for example, hydraulics are the way to go.
And then our last thing is fluids in motion. So fluids move faster through small areas than through larger areas if the overall flow rate remains constant. Fluids also vary in the rate at which they flow. So something that causes fluids to vary the rate at which they flow is viscosity. Viscosity is the resistance of a gas or liquid to flow, and it depends on particle attraction. So, for example, honey is a really thick fluid. It flows super slow. It's hard to get it to flow, actually. And so it's viscous versus water, which will flow pretty easily, is not as viscous. Fluid pressure decreases as speed increases, and this is known as Bernoulli's principle.